Hello, good evening. My name is Danko Nikolic, as you can see. I am a brain scientist originally, and I have only recently started working on AI explicitly. So what I will present to you is not much of brain science directly. You will just see some nice images of brain, which have serve no purpose. But I will talk about what I think, how we should be thinking about AI, building AI from the perspective what we have learned in how the brain works. Right? So, and what I will tell you is that actually we have to build AI in a different way than what we have been doing so far if we want to create machines that somehow approach the type of intelligence, the level of intelligence that we humans have. Now, you know probably all that if you want to teach a machine to recognize a car or a face of a child, you have to present thousands of images and so on, right? But in actually a real child, it's enough to play with one single car. And after having played with the child is able to recognize cars much better than any AI of today. Not only is it able to recognize cars, it can actually build a car from, say, Legos. Or it can actually build something new, creative, that's based on the understanding of the car. So there's a fundamental difference from doing statistics of images and from understanding what a car is about. So I'll give you an example of something that you can easily recognize as a car, if I tell you this is a car. And also a child can do it. And the interesting thing is that we can do it if we see it for the first time ever. We don't need to be trained on that. We just need to understand the concept of a car, we can do it. And now if I present you, if you understand this as a car, I can show you this image and you can immediately see a train. Today's AI cannot do it if it hasn't been already trained on trains of this kind of images. Right? And now it's even better things can happen in our minds. I can tell you now that this image is not a car anymore, but it's a table with two chairs. And you can immediately see a table with two chairs. And you see it for the first time, no problem at all. And then I can show you this image again, and then you see a classroom, right? Which was a train before. We can change our understanding of the world really quickly, really fast, and that's a big, big, big difference from what, say, machine learning today is doing, right? So I want to tell you how this happens, what are the differences here. Now, important part about the AI, how it works today, is that it stores knowledge in a big box. This could be some synaptic weights of a network, this could be some probability distribution, this could be all kinds of information. But it stores knowledge in a box, and it's a big box with lots of knowledge, and the way how it computes its answer, produces its answer, is such that you get an input in, then it computes, and it spits out the answer. The important part is that during this computation, the box cannot be interrupted. It shouldn't be interrupted. It's much more flexible and productive if it's not interrupted, if it just does its own job. Now, how did you get this knowledge in? You have a certain algorithm, certain learning rules. The interesting part about AI today is that algorithms take much less resources, much less memory on a computer. Your code of your algorithm is much smaller than the amount of memory you need to store the knowledge. The knowledge that you have created is really much larger, right? Now, the important part about the amount of intelligence in each of these two is just the opposite. The amount of intelligence in the learning rules is much, much, much higher. To create the learning rules, like say the backpropagation learning rule, to create the algorithms for deep learning, this is where the real intelligence was. This is where actually humans work really, really hard to create. Now, once you have created it, you apply it to some data, you create this big box. This is a relatively modest amount of intelligence compared to what we have in the learning rules. In a way, this little dot over there has compressed a lot of intelligence in something very short. It's like the equation of Einstein is equal to mc squared. Lots of intelligence compressed only in a little small equation, right? So this is the a very important part to understand for the later things. It turns out that if you want to make human-level intelligence with this architecture that I have just shown you, I have made some calculations. I'm not going to show you calculations. You have to just kind of trust me right now. But if you want to create human-level intelligence with this architecture, you would have to have a computer of a size probably of a planet. Because you basically have to have in this box pre-programmed everything, every possible situation, every possible thing that you could be presented with, that you could understand. Like I could come here on this beam and say all kinds of different things, and you as a humans can understand all kinds of different things. If you estimate the number of things that you could possibly understand, this amount requires huge resources if you have everything already stored in the box. So there's a problem with that. Now, I want to tell you what is the difference, how actually our brain works. We have this box of a knowledge, actually a very small box, and we have stored information in learning rules. And if you have information stored in learning rules, you can actually compress. Like we have compressed in this previous image one learning, a large amount of knowledge in one learning rule. Here we have compressed large amount of knowledge in millions of learning rules. So we can store a lot more knowledge. Now, if we divide it into lots of learning rules, what turns out that we can actually produce very intelligent system. And this follows from a so-called no free lunch theorem that tells us basically that we have to have it says any two optimization algorithms are equivalent, but their performance is average across all possible problems. But what it in practice means is that you cannot have a very general algorithm that works in all situations and to be really efficient. The algorithm either can be general and slow, inefficient, or it can be very specific for a specific situation, but then it's going to be efficient. So if you take this architecture, you have lots of specialized algorithms. And that's how our brain works. We have lots of specialized learning algorithms, probably millions of them. And that's the useless picture of the brain that I was talking about. Now comes the question, how do we create that? How do we create millions of learning rules? Well, it turns out that when we are born, we have something that we call genes. And these genes contain a set of rules, a smaller set of rules, that actually know how to learn a new learning rules. So if you have learned something about cars, and you become expert in understanding cars, we were not born with the knowledge of cars, but we are born with the knowledge on how to quickly learn all kinds of different things, and it just happens so that we can learn from this knowledge a lot easily about cars. Now, what is very important to understand about this knowledge in genes, that this is the most important part of the whole thing. This is the most intelligent part. As I told you that in machine learning, if you have algorithm that was created by really smart engineers at Google, that really their intelligence of these engineers and Google was compressed in this algorithm. Here, in the genes, is compressed the intelligence, the experience of millions and billions of years of our ancestors who have tried to survive on this planet. And not only human, but we also had ancestors as fish, and algae. Everything all together was condensed here. And this is this really powerful thing that we have. This is our E is equal to mc squared sort of intelligence. And you can't match that with some engineering and machine learning. It cannot be possibly replaced. It cannot be possibly tricked away. You cannot come up with some intelligent, creative algorithm that would replace the need for this. No way. That's the whole point. So the only thing we could possibly do is something like this. We could build an agent that has this architecture with these three levels of organization, but at the beginning it would be some very empty, without any knowledge. It would be some sort of tabula rasa. Now, what you have to do, like our own evolution did, you would have to evolve the genome of this agent. Right? And that's what we could do in the machines, right? But we don't have 1 billion years to do that, right? We would like to do it in 1 year, 5 years, 10 years, not 1 billion years. And that's possible because it turns out that it's really hard to evolve something if you have to do it for the first time, but it's much, much faster if you have to evolve something that already exists in our own genes, and you have to just transfer knowledge from our own genes to the machine genome. And I have actually come up with a whole method how can this in principle be done. And I named this method AI kindergarten because it would involve basically lots of interaction with machines and robots in a way that's very similar to an actual kindergarten. Here you go. This is an artist illustration of what this may look like. Now, there are several important implications for that. One is that there could never ever exist an AI that's more intelligent, that has better, smarter genome than us. Because all we could do is to transfer the knowledge that we have in our genes to them, and only partly. So they can never even reach our full intelligence. They can only approach gradually to our intelligence. For AI to exceed our intelligence, it would have to undergo its own evolution, have millions of years, have appropriate evolutionary pressure, and so on. There is no way, no trick that you could make this AI, or that it could make itself smarter, or develop somehow, change itself to become smarter. If it was possible, then you would violate some theorems, right? And theorems shouldn't be violated, right? So that's one important implication. The other important implication is that we can in principle develop quite an intelligent AI that is quite biological-like, quite similar to us, gradually approaching our intelligence, never reaching it, but gradually approaching it. And the process by which we have to do it is that we have to follow biological evolution, exactly how biological evolution went. Why? Because this is an experiment that has been already done, and this experiment was successful. And that's the only thing we have right now in front of us to see, to copy, to steal from, right? So we wouldn't need to do billions of years of separate evolution. So the idea of AI kindergarten is that you would have some sort of central process where you would, central server, where you would evolve the genome of an AI. You would deliver this genome to the users, like data mining people. They would use it, apply it. They would learn something from that. They would feed back information to the central server. The central server would use this knowledge, this experience, to develop even better genome, and this cycle would close. It would repeat over and over and over again. One important aspect of such organization of AI is that you can build new knowledge on top of the other knowledge. So you probably know, if you use deep learning or something today, if you train deep learning on one type of data and now you want to train it to another type of data, you cannot transfer the knowledge. If you train it to recognize pictures of birds and fruit, and now you want to train it to recognize pictures of cars and I don't know what furniture, there's no transfer. You actually have to erase this and start all over. Well, here it's not. This is not the case. Here you can actually accumulate knowledge on top of the previous knowledge, exactly how our evolution did, and exactly how our own development does, right? You learn some things as a child, and you learn new things, and you could accumulate that without having to erase the previous knowledge, right? So at some point, here in this example, you would have a point where you could actually, users would train recognition of little drawings, but then by improving the genome, the robots would be able to draw, not only to draw, but also to recognize a car, like we have given an example to you. Now, how much time do I have? 5 minutes, okay, good. So, the last thing I would like to point are two more things. One is about singularity, and one is about how to actually begin building this. So the beginning of doing this, and maybe the end of this, or the non-existent end of this. So how do you begin building such an intelligent system? So what I think we could do is pretty easily code and develop the architecture for these 3 levels of organization. That's pretty straightforward. The problem is, of course, this genome part. And we have to start with something very simple by definition, right? And I think that we could make, within a year or two, develop a genome for such an architecture that's already quite useful, that you could deliver to various data mining scientists to use for example, time series analysis, right? This product would be very different from what you have today. This product would be already certain type of expert for time series in that example. It would already have lots of experience with time series, compressed this experience in the gene, in the genome, and then once you present it with a time series, it would do much better job than what you can do today. It would learn from smaller data sets. It would be able to recognize when there is a change in a pattern, change in the stochastics of a process, and apply new genome, new knowledge. It would be much, much more efficient. It would be much like biological systems, much more similar to biological systems. And then you would start with something like that simple, go back to kindergarten, develop more genes for more broader applications, and so on. And maybe in, I don't know, 20, 30, 50 years, we would get quite close to something similar to human intelligence. Right? Never quite there, but maybe something quite close. Now, about singularity, and I said that this system cannot produce intelligence explosion, right? And then there are some theorems behind it that why it cannot produce intelligence explosion. So this means that actually singularity, as thought of exploding intelligence, would never possibly happen. And this is, I think, very good news for us, because it's a good because there's no reason to fear it, to run out of control. And the second reason is that it's not really a great reason to fear of losing jobs. Of course, this whole intelligence would be built to take over many jobs. However, since it never can really reach the level of intelligence of humans, it can never really replace human, right? So it would be more like some really dumb machine, what we would say today for some really dumb human, or something like really smart animal, right? So basically you would have lots of machines that can do lots of work, but that need a lot of supervision by human, all the time supervision. So in the world, I don't know, 50 years from now, when we have such all over such machines, basically everyone would have a job of more or less supervising such a machine. Everyone would be a supervisor. Everyone would be a boss, and I think that's a good thing, right? Thank you very much. Thank you, that's a question. Yeah, it's happening right now, of course, all the time, that machines are outperforming humans, right? So does handheld calculator multiplies faster than I do, than anyone here in this room does. So it's not a problem that machine does not outperform human. The problem is whether machine can reach human level intelligence, right? The AGI. Can you build AGI? Can you build a machine that's actually as smart as human, more or less completely as a human? That's what you cannot do. And you asked, that's what I'm saying you cannot do. Now you asked why. In one sentence, it's because what makes our intelligence is a huge amount of work that has been done for billions of years, that started in our genes, and you cannot do it in your lab.